All right. Good morning, folks. How's everybody? Everybody excited to be back? Okay, yeah, the first day back is always, the roughest, but including today, 14 school days, and you're on an even longer vacation. So there's 14 school days. Doesn't include weekends. That's true. That's true. By a little over 2.5 weeks. Yeah, not too bad. Not too shabby. Okay, so because it's been over a week since I've seen you folks, the admin asked that we quickly go through just making sure we're aware of the expectations again, especially when it comes to cell phones and the wireless earbuds. Remember, we got to keep those outside, keep those put away. If we do ever have any downtime or if we're working on an assignment or whatever the case is, wired earbuds are perfectly okay, hooked up to your Chromebook, but the Bluetooth and the cell phones, they've got to be put away. Hallways, make sure you're going to class, especially, I know everybody's trying to get to math class is the most important. Tardies, just be mindful of that. Right before the break, we had an increase in the number of tardies, so we're trying to get that number down. Smart passes, remember, you do have to have a badge, whether you're permanent or temporary, if you want to go to the restroom or to anywhere else. Remember, we're a closed campus for lunch. Not that anybody would take off anyway, right? Exactly. So there we go. And we want to show our grit, which means growth mindset, respect, integrity, and teamwork. But we didn't need that up there. We would have known what grit stood for, right? Exactly, exactly. Thank you, thank you, thank you. All right, so we went over that. Yeah, that's all taken care of. As far as this week goes, a couple things. Now, the entire week, we're going to be looking at this new lesson that you picked up. I'm going to be showing you how to graph polar functions. So we're going to be looking at a variety of strategies, getting a little more complex as we go. But tomorrow, we're going to carve out a little time in class. The Thursday before the break, I went ahead and gave you the assignment for that first lesson on polar coordinates. We're going to talk about that tomorrow. So plotting a point, changing a rectangular coordinate to a polar and back again, the distance between two polar coordinates, that little assignment packet, that's going to be due tomorrow. We'll have a quiz over that on Wednesday. Okay, so homework tomorrow, quiz Wednesday, not this material that we're starting right now. Now going into next week, we're going to be able to start the next unit, but on Thursday of next week, that's your second exam for the 9 weeks. So that exam is going to cover both lessons over polar coordinates, graphs, all that good stuff. So I just want you to go ahead and kind of have that in mind. So this Wednesday is a quiz. Next Thursday, I believe that's December 11th, is going to be an exam. Okay, but other than that, questions. Okay, well, I'm sure you folks have been looking forward to getting back to this since, that Friday we left. So I don't want to take any more time. Let's get to it. All right. So polar function graphs. Okay. So I'm going to go ahead and let you, read that. I'm not going to sit here and read through it, but I will go ahead and say, remember that our points here is going to be the radius, comma, theta. Now, normally when we're dealing with a rectangular coordinate, x comma y, x is considered your independent, so y depends on the independent value x that you choose. Well, here it's reversed when it comes to the radius and theta. Theta is the independent. The radius depends on the angle theta that you're going to choose. Okay. Now, a polar equation is an equation expressed in terms of the radius and theta. So let's start off with some basic ones. Now, you might remember back in, algebra when you were first graphing linear functions, quadratic, they were in terms of x and y. You create tables. Well, basically, we're going to go ahead and build a foundation with polar graphs the same way. So number one, it says r equals 2. Okay, so they're only giving me the radius. And we've got these same kind of graphs when we're talking about rectangular coordinate systems. We can have functions that are only x equals and y equals. They're horizontal and vertical lines. Well, let's see what happens if I'm only given the radius. Anybody think they know what kind of graph I'm going to end up with? What's that? Is going to be a circle, because the reasoning is we have a fixed radius. Now that's the distance from your pole. Remember, the pole is what we now refer to as what the origin was. Okay. Also, we'll talk about some vocabulary while we're here. We used to refer to the positive x-axis as standard position. We still rotate from it, but now we call it the what? the blank axis. First the polar axis. There we go. There we go. Okay. So while they give me a specific radius, that means I could use any angle theta that I want. So let's say I start with 0 radius. Okay. And, you know, always make sure to take a look at your increments here. So in this particular graph, every circle is 1 unit. So this right here would be 2. Okay, if I'm reading that correctly. That's kind of hazy on my scale right there. Yes, that's right. Okay. So let's say at 0, I go for a radius of 2. In fact, let's go ahead and do the same thing for each of my quadrantals. So at pi over 2, I've got a radius of 2, pi a radius of 2, 3 pi over 2, a radius of 2. And I can even go ahead and start to fill in other angles with the same radius. Okay, so 5 pi over 6, or pi over 6, 5 pi over 3, 4 pi over 3. The more of these that I put, each with a radius of 2, you'll notice I'm slowly defining that circle. So pretend I drew a much better circle. It's first day back. But there you go. If you're only provided the radius, you're going to have a circle with that radius length. Okay. So what do you think's happening in number 2 if the radius is negative? How does a negative radius even work? Like, let's say I wanted to go ahead and plot the point, okay, a negative 4.5, 0. Drake, what were you saying? It is going to be a circle, but what happens with a negative radius? There you go. So you're not going to go towards your angle. You're going to go in the opposite direction. So, for example, this point right here, with a negative 4.5, I'm going to go away from 0. So here's 1, 2, 3, 4.5 right there. And if I want negative 4.5 pi over 2, well, that would be this point right here. And then I could just do the same thing I did before. I could choose any angle with that radius of negative 4.5. So the more of these that I put, it's just going to continually give me more of my circle until I have more than enough points to see what that looks like. Ooh, that looks much better than number 1. There we go. Okay. So if I'm only provided a radius, it's going to be the graph of a circle centered at the pole. Okay. Pretty easy. It's not too bad, right? Okay. Well, let's kind of switch things up. If you take a look at numbers 3 and 4, we don't have a radius, but they give me an angle theta. What could this be? It's not going to be a circle. It's going to be what? Like an arc, a portion of a circle? Ooh, good answer, but not quite. Okay. Oliver, what were you saying, sir? A pole? Like, what do you mean? I'm sorry, sir? That's where it's going to end? Could be. Okay. Kind of think about the reverse logic of what we did with numbers 1 and 2. See, in numbers 1 and 2, we had a definite radius, but I could use any angle that I wanted, right? Well, here we have an actual angle, but that means I can choose any radius that I want. So at pi over 3, okay, I could have any radius that I want. So I could have a radius of 0. I could have a radius of 2. I could have a radius of 4, of 5.5. I could have a negative radius. I could have a radius of negative 2, okay, negative 4, all that. But the more points that I place, what's coming into shape? It's a straight line. There we go. Okay, so if you're only given the radius, you've got a circle. If you're only given theta, it's going to be a straight line. Okay, so with this in mind, go ahead and plot number 4 for me. Theta equals a negative 7 pi over 6. So really the only thing here is finding the angle that's coterminal with a negative 7/6 pi. I do apologize for the copy. Some of those didn't come out as crisp as I would like. But Okay, so because it's negative, I'm definitely going to have to rotate clockwise. So we should have found that negative 7 pi over 6 is coterminal with 5 pi over 6. Okay, so I'm looking for a straight line right here. Here we go. So there is negative 7 pi over 6 with any length radius coming off that pole. Go. How many folks got that right? Okay. Is there anything I can do to help if you're not raising your hand? Okay. Well, let's go ahead and start to kind of build off of this idea. Creating a table of values is always a good strategy when attempting to graph a new or unknown function. Okay, we're going to utilize this actually for several problems. So you've already done this previously. I mentioned linear, quadratic, probably even radical, rational, things like that. Okay, but we're going to do the same thing with an angle theta and a radius that we're going to find. So let's say number 5. Okay, I want to go ahead and find and plot enough points to find out what 2 sine of theta is going to look like. Now, before we go ahead and start getting into this with the table, I want to draw your attention to this document right here. Okay, this document lays out in general form all of the graphs that we're going to be looking at through this unit. Okay, we've got circles, limacins, roses, and bless you, we may or may not be able to get to this last column, but we'll kind of see how time plays out with that. So today we're going to be on this first column here. So if I've got a polar graph that looks like a cosine of theta or a sine of theta, looks like I'm going to be graphing a what? I'm going to be graphing a circle. That's exactly right. Now, here's the thing about this document. It has everything laid out for you right there in one spot. Now, if you want to go ahead and memorize this, I'm not going to lie, it will make things go a lot faster and easier for you. However, over the years, I've only seen a handful of students actually do that. Now, if you don't want to go ahead and commit that to memory, that's okay. That's why we're looking at these tables. You can always fall back, create a table, plot your points, you got your graph. Okay? It's going to take a little more time, but you can always do that. All right, so this is completely up to you. I would like to go ahead and run through some characteristics so that we can at least get as comfortable with this as possible. So today we're only going to be looking at this first column right here. Now you'll notice a cosine of theta, whether a is positive or a is negative, okay, that circle is running along what axis? The x-axis, right? Well, that kind of makes sense because what variable does cosine represent? It's the x variable. Okay, so if you're trying to just graph cosine with a scalar, it's either going to be to the right or left of the pole. Remember, that's the origin, the center of the graph. Well, if a is positive, it's going to be on the right. If a is negative, it's going to be to the left of the pole. What happens when I try to graph a sine of theta? Now it's suddenly running along what axis? The y-axis. If a is positive, it's above the pole. If a is negative, it's going to be below the pole. So with this in mind, I'm going to come back over here. We're trying to graph 2 sine of theta. So let's see if I can kind of predict what we're going to end up with. Should I have a circle that runs along the x or the y-axis? It should be the y-axis because we're trying to graph sine. Okay. Should it be above or below the pole? Should be above. So we should hopefully be getting some kind of circle that's going to look like that when we fill in my table. Okay. So let's see what happens. All right. So I've got everything from 0 all the way around to 11 pi over 6. So we're going to go ahead and do a couple of these together because it's good for review. So let's start with 0. 2 sine of 0. So I'm going to plug in 2 times sine of 0. See, one at a time, we're going to plug in the values given to you on the table. And if you take a look at your packet here, if you go ahead and flip to the third page, you'll notice for all the upcoming examples, I've got all of these blank tables ready to go. Number 5 has its own table, but the other one's done. Okay, so that's when we get there. Okay, so somebody help me out. What's sine of 0? 0. So 2 times 0, that's just 0. So I know I'm already starting with a point at the pole. Remember what I said at the start of the lesson? Theta is the independent. Once I plug that in, then I have the dependent radius. Okay, so let's plug in pi over 6. So now I want 2 times the sine pi over 6. Okay. Well, we already know that pi over 6 is in quadrant 1. So this will be a good little review right here. Okay. So remember, the first thing we do when evaluating a trig function is we draw the angle. Then we use that to create a right triangle. And we always default back to the unit circle. So let's say that hypotenuse is 1. What's pi over 6 as a degree? Was that 30 or 60? 30, what was across from 30? It was 1/2. What was across from 60? Square root of 3 over 2. See, we still can't escape these triangles. We're going to be with these triangles for a long, long time. So would everybody agree that the sine of pi over 6 is 1/2? Okay, and what's 2 times 1/2? 1. So right there, I've got another point on my graph. See, that's what we could do, just like you used to do back in the day. You plug in a value of x, you get your y. Here, we're plugging in theta, we get a radius. Okay. Now, to make things go a little faster, if I were to plug in pi over 3, I'm going to get a square root of 3. Pi over 2 will give me 2. Then we have a square root of 3 and another 1. Would anybody like me to plug in any of those other angles to show you how I got that radius? Any of them? No? Okay. Now, you'll notice we've still got the other part of the table to go ahead and fill in. This is where we're going to go ahead and divide and conquer. We've got 6 rows, 6 angles. Okay, so this first row right here, all 4 of you folks, I want you to evaluate 2 sine of pi for me. And we're going to go right down the road. Okay, so everybody in Vanessa's row, you're going to have 7 pi over 6. Okay, Oliver's row is going to be 4 pi over 3. Then we have 3 pi over 2. Harrison is 5 pi over 3. And then the last row by the windows is going to be 11 pi over 6. Okay. So everybody in your row is evaluating the same function. Let's go ahead and fill in this table together. Okay, I'll give you a few seconds, and then we'll go ahead and start to see what we got. Okay, so Sophia, you're doing 5 pi over 3. Everybody's okay on what angle they're working on? Okay. Noah, you good? Okay. Ooh, doesn't seem like that break just went like that. Hoping the 2.5 weeks kind of do that too. We'll see. Okay, so somebody from the first row, I'm looking for 2 sine of pi. That is 0. Okay. All right. Next row, I'm looking for 2 sine of 7 pi over 6. Okay, what is that? 1, very close. You might want to help her out. There's just one detail she's missing. Negative. -1. Okay. What about the next row? Oliver's row, I'm looking for 2 sine of 4 pi over 3. -√3. Is anybody starting to see a pattern here? What's the pattern? What should be coming up next for the 4th row? -2. Okay. Then we should have negative square root of 3, and finally -1. Okay, setting up your tables like this, where they're multiples of pi over 6 or 30 degrees, you should be able to see the symmetry. Now, symmetry is its own idea when it comes to polar graphs. We could spend a lot of time talking about symmetry. However, it's not going to be tested on the AP exam, so that's why I kind of decided just to move it to the side. You will be able to see that symmetry, though, in the tables. Okay. So does anybody want me to go back and show how I got any of those? Everybody's okay? All right. Well, let's go ahead and plot these points. Now, the only thing we're going to need, if you end up with a radical, you've got to approximate. So I know the calculators aren't out, so you just trust me on this. The square root of 3 is going to be roughly 1.73 units. Okay. So let's see here. We've already got 0, 0. Okay, right here. All right. Now we want pi over 6, 1. Okay, remember what I'm talking about using the increments here. Okay, every 2 rings, that's now 1 unit. So always be careful when you're plotting your points. So pi over 6 gives me 1. Okay, then I have pi over 3 is now the 1.73. So if this is 1.5, we're probably looking at about right there. Just shy of 1 3/4. Then we have pi over 2, 2. And then we have 2 pi over 3, 1.73, probably right about there. And then 5 pi over 6, 1. Now, the more ordered pairs I plug in, okay, like angles, I'm going to get more points on this circle, but we definitely have enough to see what it looks like. And were we correct about where our circle should have been when we were looking at that other document? Yeah. Okay. Now, there is one thing I also want you to notice about this. Okay? When we come over here and look at this table, I really couldn't show you now because it was A. We didn't know. A was just some generic value, right? We don't know if it was a vertical stretch or a vertical shrink. But if we come back over here, that scale factor is something important to that circle. What does 2 represent to that circle that we just created? It's the circle's what? Not the radius, it starts with a D. It's the circle's diameter. So that scale factor is the circle's diameter that you're going to create. Okay, so that's not too bad, right? We already knew how to evaluate trig functions. We just evaluated enough. We got points. We plotted them. We got my circle. Okay. Now, I do want to go ahead and extend on this problem a little bit because I want to tie it back into what we used to do. Now, in order to do that, I got to make sure that everybody's okay with increasing and decreasing. Do those concepts sound familiar from algebra? Where we say the function is either increasing or decreasing. So just to be on the safe side, I'm going to cover it very quickly. If we're looking at any type of function, or a relation for that matter, okay, like this one right here, this is the quadratic parent x squared. We always look at our functions, our graphs, from left to right. So we're thinking about these in terms of your x values are approaching infinity. That is, they're getting larger. Right, Dagan? Right? Right. Okay. So as we go from left to right, the x values are getting larger. But when we're talking about increasing and decreasing, it's the y values we really want to focus on. What are the y values doing? Are they getting larger, hence increasing? Or are they getting smaller? Are they decreasing? Like on this portion of the parabola right here. As we go from left to right, are those y values getting larger or smaller? They're getting smaller. So this represents where it's decreasing. So I would say that this particular function is decreasing on the interval from negative infinity to 0. Okay? But they stop decreasing at 0. What happens past 0? The y value suddenly what? They're getting larger, so they start increasing. So this would go from 0 to infinity. So this function happens to do both. Some functions might only do one, some might not do either. Depends on your function. Okay, but does that kind of make sense to folks? You remember that? Okay. Now with this in mind, let's go ahead and graph this the way we used to. Remember, I'm looking for 2 sine of theta, right? You remember how we would create a table of 5 ordered pairs and we'd go ahead and plot those? Whatever was in parentheses, we would always put that between 0 and 2 pi if we were graphing sine and cosine. And then we had those critical values, the vertical. Sine started at a 0, then had a maximum, a 0, a minimum, and then a 0. Okay, it's been a couple of months, but do we remember that strategy where we created the table? Okay. Now, we don't have to use it here, but we're essentially doing the same thing. Let's start with the parent, sine of theta. So it starts at a 0, has a maximum, a 0, a minimum, and then a 0. Okay. So this is just sine of theta. Remember, what I'm interested in is 2 sine of theta. Does that 2 represent a shift, a reflection, or a dilation? Ooh, it's been a while. What do we think? Shift, reflection, or dilation? Allison, what do you think? It's a dilation because we're using multiplication. Okay? Because it's not affecting theta directly, this is vertical. I just want to take this graph and I want to stretch it vertically by a factor of 2. So any y value that I have here, I'm just going to multiply by 2. Well, if a y value is 0, 0 times anything is 0. So those are just going to stay anchored where they're at. Okay. But what about this point right here that's pi over 2 comma 1? That point would now be pi over 2 comma 2. Okay. What about this point right here, 3 pi over 4, or excuse me, 3 pi over 2 comma negative 1? That would now be negative 2. Now keep in mind, the problem is already done. We filled in the table, we got our circle, we're good to go. I just want to connect this back to something that we've already done. These graphs that we were looking at previously, think of that as a blueprint. That's telling you exactly what's going to be happening in your polar grid. Okay? Like for example, any part of the curve that's above the x-axis, above 0, that's where your radius is going to be positive. Okay? So what do you think is going to happen to the radius if it's below the x-axis? The radius is going to be what? The radius is going to be negative. We'll take a look. From 0 to pi, every one of those had a positive radius. It wasn't until I got past pi that I started getting those opposites right there. Okay. Also, take a look at this. This little portion right here that I'm highlighting in the purple. Would you say that's increasing or decreasing? It's rising to the right. The y values are getting larger, right? Okay. Well, look what happens in your table from 0 to pi over 2. We have 0, 1, square root of 3, 2. The radius values are increasing. But what happens when I get past pi over 2? It starts to what? Starts to decrease. So all the information that we originally had in our graphs, we're seeing right here. Okay. Does that make sense? Now, you don't have to do this when you go ahead and plot these. I just wanted you to go ahead and make that connection that what we had done before still applies to what's going on now. Okay, so let's go ahead and do another one of these. Okay, let's skip to number 8. Yeah, we're definitely going to start skipping around a little bit. Okay. Let's say I want to go ahead and graph r equals 4 cosine of theta. Okay. Now, we're going to go ahead and fill in the table and all that in just a moment. But again, let me show you the importance or why this right here can be so useful to you. Okay. So 4 cosine of theta. Am I going to have a circle along the x-axis or the y-axis? How do I know? Because it's cosine. So where should that circle be? Should it be to the right or to the left of the pole? What's that? To the right or to the left of the pole? How do I know? The 4 is positive. And what should the diameter of the circle be? So I should be getting a circle that looks something like that. Okay. See, already having knowledge from that other table, that little reference sheet, I already know what I'm going to end up with. Okay. But if you don't commit it to memory, well, then you can just do like we're about to do. Let's do a table. Okay. Let's go ahead and plug these in, starting with 0. So I want 4 times the cosine of 0. So let's see here. Soren, what's the cosine of 0? Oh, now 0. One. There we go. So this is going to be 4 times 1. So my first radius is going to be 4. Yeah. Sure. Get you back. Mm-hmm. Okay. Does anybody want me to diagram that? It's a quadrantal, but I can show it very quickly. Okay, let's do one more of these. Let's do pi over 6. Okay, so now I want 4 times the cosine of pi over 6. Well, we just saw this triangle a moment ago. Okay, we created a right triangle with that angle. Remember, across from pi over 6 was 1/2. Across from the other angle was square root of 3 over 2. So this time, what's the cosine of pi over 6? What is it? Isn't it root 3 over 2? Now, what's 4 times the square root of 3 over 2? 2 root 3. Because the 4 halves, yeah, they're going to cancel. So I'm going to get 2 square root of 3. So that part of it, that's nothing new. We know how to evaluate a trig function. We plug in, we got some points. Okay. Now, if I keep plugging in, pi over 3 will give me 2. Pi over 2 will give me 0. 2 pi over 3 is a negative 2. And 5 pi over 6 will give me a negative 2 square root of 3. Now, we could also plug in the angles from the second part of the table, but what did we already learn from the previous example? What kind of radius value should I have? Like if this one right here is a 4, what would this one be? Negative 4. At 7 pi over 6, I should have a negative 2 square root of 3. Remember, in the second part of the table, each radius will be the opposite of what you saw in the other one. Okay. Just like that. All right. So now we got our points. All we need to go ahead and do is plot them, and then we can connect them with a smooth curve. Okay, so we do need to know what 2 square root of 3 is, and I've already got that taken care of for you. So 2 square root of 3 is roughly a 3.46. Okay, right, Drake? Right, Drake? Right. Okay, fantastic. All right. So I know someone's probably been thinking about this all week. Who wants to come on up and plot these points for me? That's all you got to do is plot the points. First day, we got to use the Wheel of Destiny. Mason, what do you think? Mason, you with me? He's with me. Okay. All right, we're going with the Wheel of Destiny. Okay. Oh, okay, let's go ahead and sort this out. So in here, we got to get to 29, 25, 26, 27, 28, 29. Okay, let's take that out. Okay, let's give this a good shuffle. Shuffle a couple more times. Here we go. So there's no math. All you got to do is plot points. The first half of that table. Oh, Ethan! It's like winning the lottery. Come on. Okay, so Ethan, all you have to do is go ahead and plot these first points for me. And remember, 2 root 3 is 3.46. Oh, you got to use your finger. Yeah, I don't have it.
Okay, so the first one is 0, 4.
Okay, so go ahead and hit this marker button right here. There you go. Try it now. Okay, so there is 0, 4.
Over 6, so it's 3.4, so about like 3.5. Oh, wait. Is it erased?
There you go. So 1, 2, 3. So about 3.5 right there. Okay. Pi over 3 gives you 2. Pi over 2 is 0. Remember, with a negative radius, we go in the opposite direction. Okay. And then at 5 pi over 6. Okay. There we go. Okay. Here we go. That's all there is to it. So we were correct. We should have gotten a circle right there to the right of the pole along the x-axis. And what's the diameter of that circle? It is 4. It's that scale factor. Okay. All right. So if you remember what's on that reference sheet, it makes this super easy. Like if I were to come up here, let's say I wanted r equals cosine of theta. Okay, well, cosine, it's got to be along the x-axis, so the right or left of the pole. What do we think? James, what do you think? To the right. Okay, what would the diameter of the circle be? Okay, 1, because that's what the scale factor is, yeah. So I'm looking for something that probably looks like this. But if I were to fill in a table, I'm going to get points exactly for that function. So how are we doing? Anybody having a hard time? Okay. Cool. Well, all right, we got one problem left, and then we're done. I know, I'm sad too. Okay, so we'll go ahead and get that back over here. Okay, so let's take a look at number 9. Ooh, that moved over. Okay, so number 9 to 11, we're going to start looking at cosecant and secant. Okay, so with a scale factor, just like we were doing with sine and cosine. But unlike sine and cosine, we're not going to get the graph of a circle. Okay, we're going to get something else. Now, I've already got the table right here. You'll notice this table, this is for number 9. See, what I've done is I plugged in 0, pi over 6, and I got the corresponding radius. Okay. If anybody would like me to plug in any of those and show you how I got that radius, I can definitely do it. So I'll give you a second to go ahead and jot that down. Remember, you've got that page where you have all of those blank tables. Got your bachelor? Yep. And again, you'll notice going from the first table to the second table, the radius values change signs. Okay. So technically, you only have to fill in half the table, and you already have the other half. Remember, we're doing this in increments of pi over 6, though, 30 degrees. Okay, so I'm going to give you a few more seconds to go ahead and copy down each radius value. Then we're going to go ahead and start plotting those points, and we're going to see what is it that we end up with, what kind of graph, and why. Is everybody good, or we need a few more seconds? Okay. Now remember, some of these are not going to work. Remember, because cosecant, along with several other graphs, they have asymptotes. So there are places where the function is going to be undefined. Okay. So I can't do anything at 0, but at pi over 6, I've got 2. Okay. Now be careful, going from number 8 to number 9, in this polar grid, every 2 circles is 1 unit. Okay. So we want to first go ahead and find, let me scroll up here, pi over 6 gives me a radius of 2. So I'm going to go ahead and put that one right there. Okay. Now at pi over 3, I need 2 square root of 3 over 3. Well, you might have noticed that in the upper corner, kind of cut it off, I've already given you the approximation for that radical expression. You're looking at about 1.15. Okay, so 1.15. So pi over 3, so we're going to go just a tiny bit past 1 right there. Then at pi over 2, I've got 1. To pi over 3, I've got the same decimal. So let me do this. There we go. And then at 5 pi over 6, I've got a 2 again. Okay. Now, it's not perfect. I mean, this is just a sketch. But what does it look like is forming? A line. All of these points are going to be collinear. You might be wondering, well, why is graphing, cosecant or secant going to give me a line like this? Well, I'm glad you asked. Okay. We got r equals cosecant of theta, right? Well, let's define sine. We know that sine of theta is y over r. Would everybody agree? We were looking at that a long time ago. Solve that for r. What would the radius equal? So sine of theta equals y over r. If I rewrote it, what does r equal? Ooh, a lot of people talking. I can't understand. Anybody? I'm sorry? Sine of theta times y? Not quite. Y divided by sine of theta. Now here's why this is important. We're trying to graph r equals cosecant of theta, right? Well, now that I know what the radius equals, why don't I take this expression and go ahead and substitute it in? And instead of saying r equals, I'll go ahead and say y over sine of theta equals. And then we have cosecant of theta. So let's say I want to go ahead and now just have this y equals. How can I get rid of that sign? Yeah, just multiply through by sine of theta. So see, sine of theta times y over sine, those cancel. There's y equals. Think about your identities. What's sine times cosecant? Remember, what's their relationship? They're reciprocals. So what happens if you multiply reciprocals? If you only have a y in your function, was that a horizontal or a vertical line? It was horizontal. See, we ended up with y equals 1. So we can already kind of think about this. If cosecant is going to give me a horizontal line, what would it make sense that secant is going to give me? A vertical. Yeah. Okay. And we'll actually see that tomorrow for the first time. Okay. But how are we doing? First day back, not too bad. We missed pre-cal? I can tell. Okay. We got 5 minutes. All right. Let me go ahead and get this out of the way. Interesting chicken. Okay.